Hello everyone, and thanks for your interest to this webinar. I'm Ehsan, Dr. Ehsan Moradabadi. For those who might not be familiar with my background, I'm an experienced civil engineer with expertise in both structural and geotechnical engineering. My focus is on environmentally conscious design, technical solutions, and feasibility studies using computational modeling. Let's kick off by discussing our main goal for these type of webinars. One of the aims of this type of webinars is to encourage collaboration and learning across various sectors. I'm excited to announce that I have over 350 registered attendees for this webinar. They come from diverse backgrounds, engineers, academics, researchers, and students, all joining in from around the world. Let's embark on this exciting journey together, fostering collaboration and knowledge exchange across diverse fields with our 350 plus attendees from around the world, globe. Today, I'm diving into a groundbreaking concept, physics informed digital twin. I'll kick things off by exploring what these models actually are. After that, I'll explore the benefits of using them in the tunneling industry and beyond. Then we'll talk about how to combine physics-based knowledge with data-driven insight with real examples in tunneling. I share real-world examples of how digital twin models boost efficiency, safety, and cost effectiveness in tunneling projects. I'll also look at how digital twin models can improve efficiency, safety, and cost effectiveness in other geotechnical projects like offshore wind farms and renewable energy projects. I'll then explore the potential solutions for limitations of using these models and conclusion and questions and answers at the end. But before I explore the intricacies of digital twin, let's briefly touch on a dynamic realm that has captured imaginations worldwide, the metaverse with 400 million active users. Imagine an interconnected universe where avatars roam freely, economic thrive, and creativity knows no bounds. A collective space where virtual experience unfold without the constraints of physical limitations. Unlike the metaverse, which is a digital collective, digital twin, sometimes called iTwin, precisely mirrors manufacturing parts, real-world assets, systems, or processes. It bridges the gap between the physical and digital realms, enriching our understanding and aiding decision making. In particular terms, an asset twin is a virtual representation of a physical asset that spans its life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to help decision making. A digital twin typically uses engineering design data like specs, drawing, beam models, and analyzes and operational data from information of things feeds, sensors, drones, cameras, and LiDAR scanners. It also incorporates other information such as asset tags, work orders, and maintenance and inspection records to create a visual representation of assets. This is made possible by advances in 3D extended reality, 4D modeling of change, AI analytics, and machine learning. Let's dive into the fascinating world of digital twins and explore their application and benefits across various disciplines. In this presentation, although I discuss digital twin in general terms, my primary focus centers on its application in tunneling in this industry, specifically tunnels and their relevant infrastructures as physical assets. Digital twins provide real-time optimization and monitoring of physical assets without extensive system changes. The digital twins technology opens up an exciting avenue for conducting accident and hazard analysis in the context of tunnel life cycles. These analyses involve in systematic examination of processes or operations to pinpoint potential hazards and operability issues that might result in non-conforming outcomes. They can use for fine-tune office layout and safety measures by using virtual models. Augmented reality and digital twins streamline maintenance training. They simulate economic scenarios for informed decision making. These models predict equipment failures for proactive scheduling. They optimize logistics and identify bottlenecks. They analyze energy consumption in operation of the asset. They can use to inform urban planning decisions virtually. They may use for enhancing store layouts and track foot traffic in stations. They can optimize products' performance, such as rail cars, TBMs, and so on, and identify inefficiencies and reduce defects. They aid in drainage design, water and wastewater management. They simulate mining operations and assess impacts. They can use to monitor and analyze safety, health, and well-being of underground workers. They can enhance educational experience with interactive simulations. They can revolutionize atmospheric and climate science, enhance medical decision making, improve engineering processes, and aid sustainability efforts by reducing material usage and improving product traceability to minimize environmental waste. And if you weren't already convinced by the 16 benefits and application mentioned in tunneling and in general, here's something interesting. The global digital twin market is expected to experience substantial growth. Projections indicate that it could expand from 11.51 billion US dollar in 2023 to a whopping 195.85 billion US dollar by 2030, about 25% of AI market size. These impressive numbers are given by compounded annual growth rates between 35.7% and 45.1% as reported by different reliable sources. Let's compare this with the global tunnel construction market that was valued at 88.65 billion US dollar in 2021 and is projected to reach 194.06 billion US dollar by 2032, just below the line for digital twin. Exploring the origin of digital twins across different time periods, we find fascinating development that spans several decades. In 2002, Michael Greaves took the stage proposing digital twins as a powerful model for product lifecycle management. He introduced these digital replicas as doppelgangers that help us understand and optimize physical products. John Vickers in 2010, as part of NASA's Brain Trust, officially labeled these virtual replicas as digital twin in a roadmap report, having introduced them as cosmic twins, mirroring space systems. But wait, even before that, back in the 1960s, NASA was dabbling in basic twinning ideas for space programming. They created physical duplicates of systems to simulate and troubleshoot. Fast forward to today, by emerging and developing technologies like 3D visualization using extended reality, 4D timelines, and sprinkle some artificial intelligence and machine learning, digital twins have become stars in the constellation of the Internet of Things, transforming science fiction to reality. Now let's explore how to create a digital twin for an asset. First, we need to gather project data from different phases of a physical asset lifecycle. This data serves as the foundation for simulation and building a digital replica. During the construction phase, we take things up a notch. We integrate the physical asset with its digital counterpart, both horizontally and vertically. This integration enhances the overall system performance. Once construction is complete, we focus on as-built information. Having accurate details about the asset after construction ensures that our digital twin closely mirrors the real-world counterpart. Next, we leverage cloud computing. With the wealth of data, cloud platforms allows us to efficiently process sensors data through an Internet of Things framework. Analyzing behavior is crucial. By synchronizing sensors data with the digital replica, we gain insight into how the system behaves. This knowledge enables us to make new predictions. Lastly, we continuously update our predictions throughout the asset's life cycle. Chronological records from sensors keep the entire process current. Now we are ready to distill the essence of digital twins and their evolution throughout a project life cycle. Digital twins are captivating entities that mirror the growth of a project akin to a child, maturing over time. Initially, during the conceptual design phase, they exist as simple 1D or 2D representations, a blueprint of ideas and potential. As the project advances, these digital twins evolve into more intricate forms. By the construction stage, they transform into robust 3D and even 4D models. These multi-dimensional twins not only capture geometry but also track behavior over time, enabling us to simulate and optimize real-world performance. Just like a child's journey from infancy to maturity, digital twins adapt and enhance our understanding alongside the project. Their chronological maturation parallels that of a living organism, bridging the gap between static geometry and dynamic behavior throughout the project lifecycle. So when you first encounter digital twin, you might think, hey, this isn't groundbreaking technology, and you're not wrong. We've already talked about many of the underlying concepts, but here's the twist. Digital twin models, much like large language models, are more like discoveries than inventions. Remember what Jeff Bezos once said about chat robots? He described large language models as discoveries rather than inventions. And that's precisely how I see digital twin models. They're like the telescopes of our digital universe. Telescopes were invented years ago, yet we are still exploring the cosmos and constantly improving our tools for this grand exploration. So let's embrace the familiarity, appreciate the iterative progress, and dive deeper into the fascinating world of digital twin by exploring predictive analysis in digital twin, the beating heart of this presentation. In this section of the presentation, I have no choice but to delve into the mathematical aspects of physics-informed models. However, rest assured, I strive to explain it in the simplest term possible for our general audience. We recognize that not everybody is interested in the nitty-gritty details of the solution. Additionally, we can organize follow-up webinars to explore this topic further. When we want to predict how well an asset, system, or process will perform, we can use a mathematical function that represents its physical behavior. Imagine this function as a way to model the system under investigation. Here how it works. We have performance function, f. This function describes how the system behaves. We'll call the output of this function y, which represents a vector or an array of performance-related variables. X's are input variables. Think of these as the factors that influence performance. They form an array, and each component of this array corresponds to a specific input parameters vector. And we have deterministic parameters D. These are fixed values that affected the system. Like X, D is also a vector with its own components. In engineering problem, we have performance criteria O. The vector O contains criteria that defines how well the system should perform. For instance, if we are assessing a cantilever beam, O might include a baseline value for a maximum moment the beam can withstand. Now let's consider a simple example evaluating the maximum moment of a weightless cantilever beam. The maximum moment depends on the point load at the beam's end and the beam's length. We are usually confident about the beam's length, but the point load can vary. So our X vector has one component, the point load, and the D vector also has one component, the beam length. When we apply different point loads, say 3 different loads or 3 different samples, for example, I is equal 3, we get 3 output. Y has 3 components, 3 output samples, I mean. If the maximum drive load is below the performance criteria, the system operates successfully. If it exceeds this criteria, it's a failure. Now consider other scenarios like beam settlement at the end. So let's add another index J. This representation can handle any scenarios with any number of input parameters or performance functions. Additionally, if the performance function is a probabilistic representing by index k, solving it multiple times with the same x vector may yield different y values. This mathematical representation allows us to comprehensively model performance across various conditions. In the context of digital twin models, our goal is often to create a digital representation that closely mirrors the reality, a kind of replica. However, when it comes to mathematically describing system performance, things aren't always as straightforward as the classic cantilever beam example. Typically, we lack a neat closed-form solution or a well-defined output probability function for the system, especially when dealing with computational models like finite elements or finite difference methods. Traditionally, we employ sophisticated software packages to computationally model the performance of physical assets under investigation. We'll refer to this as the modeling steps. The parameterized model derived from computational modeling operates similarly to the function described earlier for cantilever beam example. For specific input parameters, we obtain a corresponding output performance prediction. However, when dealing with highly complex systems, identifying the input and output of each submodel isn't always straightforward. This challenge becomes even more pronounced when input parameters are influenced by various sources of uncertainty. We can think of this step as quantifying the source of uncertainty. In this phase, we identify the parameters that need to be modeled probabilistically. When we work with advanced computer models and rely on sample-based solutions, even if we speed up simulation using cloud computing, we often encounter a challenge. Solving the performance function for a replica of a real-world physical asset can be computationally expensive or even impossible with a reasonable time frame. That's when computational optimization comes into play. We explore ways to improve efficiency. Sometimes we use surrogate model standing for our main computational model that requires less computational power but less accurate. Think of it as a cost-effective alternative. When we have more reliable information for our input and output variable, we can use Bayesian updating to adjust our variables accordingly. Let's continue our discussion in application of these models in construction phase of a tunnel. Imagine this, we are on a tunnel project surrounded by diverse geotechnical data index. Instead of fixed absolute, we grapple with a range of values during design and assessment. But here's the twist. For those lengthy projects, we often have limited borehole data and its accuracy might be questionable due to human and machine error. So how do we play safe? We might need to scale up parameters or tweak our design result to ensure safety. However, this cautious approach could lead us away from optimal design solution. Now picture this. As we start digging, we step into uncharted territory, a whole new world of data. Sometimes the values we encounter aren't even as conservative as we expected. These unexpected variations can significantly impact our design decisions and overall construction strategy. So what's the solution? We need an approach that accounts for uncertainty at every phase of the project. This means constantly updating our knowledge and refining our predictions. And that's where the physics-informed model we discussed earlier comes into play. It enables us to consistently and precisely predict tunnel performance behavior in real time. Consider the context of digitally constructing a tunnel using digital twin framework. For example, a tunneling induced damage model, as you see in a decision analysis diagram here. During the planning stage, we often rely on experience, investigation, and measurements from lab and institute tests to estimate input variables. Output variables, on the other hand, remain uncertain. As the asset progresses through its life cycle, whether during construction or operation, we may collect additional data for modeling the physical asset. Information of things sensors play a crucial role in measuring both input and output variables. Depending on the asset phase, we might need to update our predictions. Sample-based algorithms such as Monte Carlo-based method and Bayesian updating come into play for propagating uncertainty for initial prediction and updating the prediction, respectively. I must admit that a comprehensive grasp of these concepts might require additional study and reading. If you're really keen, I recommend checking out my PhD thesis. It delves into the underlying principles of this approach. Let's delve deeper and explore the practical application throughout a real-world case study. Please note that this is only an overview of the modeling regarding the purpose of this presentation. So we are looking at a horseshoe-shaped shallow roadway tunnel located beneath a densely populated area in the southern part of Tehran. This tunnel stretched for 1.5 kilometers and was excavated in soft ground composed of alluvium soil. To understand how are the variation of soil parameters along the tunnel, a 3D soil model was created. You can see 4 critical soil parameters of the ground as an example, which we obtained from limited boreholes, in situ tests, and laboratory experiments. The tunnel construction followed a sequential excavation method to simulate the ground behavior during excavation. Simple parametric finite element models were developed. For simplicity, it was assumed that the ground is homogeneous. These models have 28 input variables, and one of its main purposes is to estimate the surface settlement caused by tunneling. The goal with this simulation is to construct a reliability curve for the maximum transversal surface settlement and to ensure that the system performs well according to predefined criteria for settlement of the road above the tunnel. First, a local sensitivity analysis was conducted. This step helps us to verify that our finite element model accurately presents the tunnel's behavior under both nominal and extreme parameters values. Next, a global sensitivity analysis was performed using the Monte Carlo-based Latin hypercube algorithm. All 28 parameters were considered, and by conducting around 500 simulations, it was found that only 10 parameters significantly affect the result. The uncertainty ranges for the other parameters didn't contribute much to the variation in the outcomes. By reducing the model dimensions from 28 to 10, we not only save computational resources but also gain better interpretability. Let's delve into the computational aspects. This straightforward finite element model allowed to run simulations on an old desktop computer without using either parallel or cloud computing under 5 minutes per iteration. With reasonable samples, around 1,000 iterations of the 10 critical variables, each simulation was completed in less than 3.5 days. However, when dealing with more intricate 3D models, even with cloud computing, the computational cost can become prohibitive. That's where surrogate models come in. I leveraged the output from the global sensitivity analysis to create an artificial neural network surrogate model. This approach enabled me to compare results between the surrogate model and the original finite element simulation, as you can see in this diagram. Keep in mind that this study wasn't conducted during construction. Instead, we had monitoring data available, which allowed me to update the prediction using Bayesian updating method. The same methodology could be applied during construction, continuously adjusting input parameters and output results. Let's take a closer look at how this method works for a more complex tunneling problem. Here we're looking at a cross-section of the Rio Piedras station, which is part of the Tren Urbano subway tunnel in Puerto Rico, US. The underground cavern of this station is shaped like a horseshoe and measures 70 meters wide, 60 meters high, and 150 meters long, with two 30-meter access shaft and at either end excavated in alluvium soil. To minimize the impact on the structures above, the tunnel was built using the stack drift method, with drifts measured 3 by 3 meters. The aim of this case study was to test how well the method could handle uncertainties in input parameters, like the spatial variability of soil properties, and to create a reliability curve for maximum transversal settlement and volume loss. A new geostatistical analysis was done to build a 3D soil model, which helped us understand the spatial variability of the soil. Here you can see the mass density function and the fitted probability density function for different soil characteristics, aligned with a visualization of their variation along the tunnel's length. Similar to a previous case study, a parametric finite element model of the tunnel was built. A univariate homogeneous Gaussian discrete random field algorithm was used to map the spatial variability to the model, creating a random inhomogeneous parametric finite element model. Remember when we talk about the performance function and its random nature? Here our finite element model was turned into a probabilistic model, meaning that running the model with the same input variables could give different results each time. In terms of computational effort, a single simulation of this model takes more than 49 minutes on the same computer that took only 5 minutes for a previous case. Given the probabilistic modeling and the number of variables, running 10,000 simulations for a preliminary sensitivity analysis would take about a year on the same computer without cloud computing. To tackle this, we did a local sensitivity analysis to find the influence area of the random field and optimize the mesh to reduce computational costs, mapping the random field only to the influence area. This new model ran 6 times faster. However, this wasn't enough to solve the problem, as practically each simulation still have been taken over months with 2 computers, and we weren't confident that this would be sufficient, and we needed to ensure enough simulations to get reliable results for the random finite element model. We optimize further to find the effective number of simulations needed. Here you can see a graph for 1,000 simulations with nominal values, showing maximum transversal settlement versus the number of simulations. It indicates that only 15 simulations are effective for this model, significantly reducing the number of simulations needed for appropriate results. The final sensitivity analysis was done with a sample size of 200 equivalent to 10,000 simulations. These case studies highlight some practical challenge we will face with the computational effort needed to solve these types of problem, and they also offer some specific solutions to tackle this challenge. While interpreting the results beyond the scope of this presentation, feel free to explore my PhD thesis if you're curious. Alternatively, we could organize webinars for a deeper dive into the detail. As we discussed earlier, whenever we talk about a digital twin, we aim at digital organism that possesses an intricate anatomy that allows it to predict the future behavior of the asset it represents. Think of these finite element models as physics-informed predictive models that were specifically designed to assess tunnel damage. However, you could apply a similar approach to any type of excavation method like mechanized tunnel excavation, any other architecture, engineering, and construction simulation, or hazard and operability models when dealing with the entire life scan of a tunnel. The other point is, in simpler terms, for these models or case studies to be considered a digital twin, it should have been developed during the project's construction phase, using the chronological data from the project's beginning and being updated with real-time data. Additionally, it's crucial to be integrated with other AEC simulations and BIM models. Now that we've uncovered the inner working of digital twins' predictive capabilities, let's explore its application through various global examples. Upon examining research papers and tunneling projects post-2017, we've observed a noticeable surge in the adoption of the digital twin concept in both academic studies and practical projects. This Google Trend graph clearly shows a rise in interest for digital twin in science, indicating that the topic wasn't popular before 2017. However, before that period, we could approach the subject through related topics like the Internet of Things and predictive analysis as shown in the Google Trends graph. Here is a quick look at some recent studies as examples. In a case study done by researchers from Brazil, they used a digital twin method to predict tunnel performance by inspecting degradation. They used data from visual inspection done by the railway company in northern Brazil. This railway connects the northern and northeastern region for ore transportation and includes various rail infrastructures. The framework assess degradation processes in tunnel like chemical interactions with the environment, aging and wear of material, and accidental events like mechanical shocks, fires, and explosion. In another work, researchers from China and Singapore used a digital twin framework to study real-time advanced control of TBM operations in Singapore Circle Line 6 project. Other project is the Wenyi Road Tunnel in Hangzhou, China, opened in 2018. It's claimed to be the first tunnel to use life cycle operations and maintenance management. The tunnel has 4 working walls, 2 ventilation towers, a management room, and a service room. The electromechanical system in the tunnel is quite complex, with various important components like fans that help remove harmful gases and control visibility. In 2021, researchers from China and the United States develop a digital twin-based decision analysis framework for managing tunnel operation and maintenance. They also use the same methodology to predict the performance of highway tunnel and so on. Korean researchers studied a digital twin-driven framework for predicting, visualizing, and monitoring of TBM performance using machine learning. Researchers from Germany used an experimental digital twin to study tunnel ring buildings erectors. Their study showed that their digital twin can successfully help build tunnel rings and optimize the control policy for fine adjustments, especially when placing the last ring segments. Researchers from Italy, Portugal, and Slovenia use real case studies in Europe like the cooperative intelligence transport system and the road tunnel scenario to show how useful a security digital twin can be used for protecting critical infrastructures. Let's take a look at how other researchers have applied the digital twin framework to fields related to geotechnical engineering projects such as offshore wind farm and renewable energy power generators. Researchers in Norway have created a digital twin platform that helps users gather, visualize, and analyze data in real time. This platform aims to enhance predictive capabilities, supports better decision making, reduce potential failures, and improve reliability. It starts by collecting real-time data from sensors. Users can choose to view the results in 2D, 3D, or even augmented reality depending on their needs. To test this platform, the researchers focus on predicting failures in wind turbine bearings. They use the setup of the high wind Tampen floating wind farm. The platform equipped with the prediction algorithm uses vibration and temperature data to monitor and predict failures. The prediction method has shown promising results thanks to performance indices from experiments and research studies. In another study, researchers from China came up with a framework using digital twin technology to tackle the challenge in the life cycle of floating wind turbines. They aim to solve issues like the lack of a unified method for gathering and integrating information, the complexity of achieving global simulations and optimization, and the need for systematic state monitoring and inversion. They use real data from the entire life cycle of a 60 megawatt floating wind turbine, from installation to operation, to demonstrate how effective their method is. They followed the operation go on. In Australia, researchers look into using computational efficient surrogate models within a digital twin framework to predict fatigue failure for bolted joint configuration beyond offshore wind turbines support structures. Researchers in Denmark propose a digital twin framework to analyze how uncertainties like soil stiffness and wave loading affect the reliability of fatigue damage. This helps optimize decision models for maintaining and operating existing structure as well as designing new ones. In another study, researchers from the UK and Italy demonstrates the effectiveness of a digital twin framework by using operational data from the world's first commercial floating wind farm. They tackle two main issues: detecting long-term drifts in the mechanical response of the mooring lines and predicting the near future actual tension of these lines. To wrap up our discussion for this section, let's look at examples in other types of renewable energy projects. There are many projects and studies out there that could be useful for your future endeavor. For instance, Korean researchers have developed a digital twin for the Yongsu wave power generator. This prototype is being tested in the coastal water of Jeju Island in South Korea. The power generator itself is a fixed type concrete box structure with an open chamber room. It uses an oscillating water column system to generate electricity by converting the up and down movement of water in the chamber into electrical energy. The digital twin simulation even includes non-structural mass components like ballast and the added mass around the structure, making the model more accurate and realistic. The project is still ongoing and researchers are measuring various uncertain factors such as the mechanical properties of materials and hydrodynamic coefficients to fully bring this model to life. In another study, researchers from Sweden and Norway created a digital twin model to speed up the calculations needed for a CFD prediction model. This model helps estimate the mooring forces on a point absorber wave energy converter during extreme wave conditions. We've already discussed some of the computational challenges involved in solving physics-informed models. When it comes to implementing digital twin framework, we face several additional challenges. Remember, this overview only touches the surface, and each point needs deeper exploration by relevant experts. In the end, practical solutions must be tailored to the specific themes of each project. When putting together a project team for digital twin, one of the challenges is finding the perfect blend of individuals. We're looking for versatile team members who can handle a variety of tasks, connect different pieces, and spark creativity. At the same time, we need multidisciplinary experts who bring deep knowledge to a specific area. Now, while I won't delve deeper into this topic during our current presentation, I can tell you that in general, fostering collaboration, networking, and providing targeted training can help address the shortage of experts. When it comes to infrastructure assets, we're dealing with massive amount of data from various sources. Let's consider a digital twin application relevant to the seismic performance analysis of a tunnel, for example. In this scenario, we're dealing with an enormous amount of data sourced from photogrammetry, GIS, information of things devices, and sensors. What is the challenge? These data sources often exist in separate silos, making it overwhelming to manage. So the solution lies in adopting an open, scalable, and vendor-neutral platform. While I won't dive deeper into this topic here, exploring such a platform is essential for efficient data management and decision making. AEC industry places a strong emphasis on accuracy and reliability, which often leads to a conservative mindset. However, when it comes to digital transformation, the AEC industry might lag behind other sectors. The solution lies in fostering collaboration, breaking down silos, and actively promoting digital transformation initiatives. By doing so, we can bridge the gap and embrace technological advancement more effectively. Digital twins rely on BIM as a powerful tool, but sometimes getting all the information online can be a bit tricky. But fear not. The solution lies in digital alignment, keeping a close eye on changes and ensuring everything syncs up nicely. By doing that, we can tackle the challenge head on. To achieve success with digital twin, a collaborative approach involving a multidisciplinary team is essential. This team should include visual designers, engineers, building information modelers, architects, and clients. Effective communications among team members, when each bringing diverse perspectives, is crucial for aligning with the project's objectives. Now let's talk about leadership style. Autocratic and paternalistic approach don't work well in digital twin teams. They create a climate of fear and hinder open dialogue and independent work. On the other hand, purely democratic leadership can lead to decision-making paralysis due to conflicting viewpoints. The sweet spot lies in a consultative leadership style. These leaders emphasizes task orientation and build a strong interpersonal relationship with the team. They rely on team members' expertise and collaboration with external partners to make informed decisions. This approach ensures adherence to project timeline, budget, and constraint. ISO 44001 introduces a fresh approach to this type of leadership, emphasizing behaviors, organizational culture, and management processes. It acts as a bridge connecting organizations across borders, enabling sustainable business relationships and unlocking the advantage of collaborative working. Lastly, the effectiveness of digital twin hinges on high quality data, requires comprehensive standardization across information technology, data quality, and data supply. When dealing with the extensive data in digital twin, robust cybersecurity measures become crucial. These measures protect against unauthorized access, theft, or damage to hardware, software, and electronic data. To ensure effective management, consider implementing an appropriate system like ISO 27032 as an example. A digital twin model behaves much like an organism as mentioned before. When dealing with a complex model, a system generates an immense volume of data. While AI can assist in maintaining constant calibration with physical assets, the critical task of interpreting this data for decision making ultimately rests with humans. Think of it as a patient undergoing surgery. Having appropriate standardized project-specific indicators is essential to keep the asset under control. The other challenge of digital twin are cost of building infrastructure of cloud computing and energy cost of operation. Remember that digital twin technology and cloud computing infrastructure are in synergy. Their symbiotic cycle ensures that improvement in one directly benefit the other. And now explore some potential solutions for addressing the challenge of cloud computing infrastructure costs and energy consumption when implementing digital twin. By optimizing design of data centers, cooling systems, and hardware, or using renewable energy sources, it is possible to reduce energy consumption. Visualization and containerization allow better utilization of physical servers, reducing the need for additional hardware. Dynamic resource allocation ensures efficient use of computing resources. We need to develop algorithms that consider energy efficiency during resource allocation, workload scheduling, and data movement. Machine learning and heuristic can predict CPU utilization and optimize virtual machine placement. It's better to distribute processing closer to data sources to reduce data transfer and central server load. Edge computing minimize energy intensive long distance communication. Real-time monitoring tools track energy usage and identify inefficiencies. We can implement automated energy saving policy based on workload demand. We can choose cloud providers committed to sustainability and energy efficient practice. Some providers offer regions powered by renewable energy sources. We can combine public cloud services with on-premises infrastructures. Migrate workload to the cloud selectively, optimizing costs and energy usage. Remember, for a deeper dive into these solutions, expert consultation is essential. Let's wrap up our discussion today by reflecting on what we've explored. I gave you a brief overview of the concept, but it's essential to recognize that this is just a starting point. In this webinar, you'll gain insight into digital twin and how predictive analysis and physics-informed modeling play a crucial role. This approach has immense potential for enhancing our understanding of physical asset design and management, especially in the context of tunneling and other geotechnical engineering projects. Now let's shift our focus back to the metaverse platform with a whopping 400 million active users in the entertainment industry. There's significant interest and potential among people from diverse backgrounds and knowledge domains to contribute to digital twin technologies development. Not only can this be an enjoyable endeavor, but it also provides an environmentally friendly solution for preserving our material resources for future generations. Remember, our journey has just begun. Let's embark on this exciting path together. The secret to unlocking success lies in fostering collaboration, both close to home and across the globe. Thank you for joining me on this insightful journey. We have a couple of minutes for questions and answers. The webinar will last for an hour and the live video will go offline automatically after that. I noticed that the replay will be publicly available on LinkedIn and not everyone might want their questions answered live. But don't worry, I'll stick around for an extra 30 minutes to answer any questions you have. I provide now a link that we can continue discussion there. You can alternatively reach out to me by messaging or by dropping a comment under the replay video post later. Thanks again for joining this webinar and I hope everyone has a great time.